Go ahead and start. So just a couple of things. Let me share. Don't forget to share I'm not on mute. Hopefully this is going to work. We put this here and now it's working. Okay. So first of all, I wanted to talk a little bit about PyTorch. So what's the difference between what is it called? TensorFlow and PyTorch. So basically, I think in general, TensorFlow. Well, first of all, TensorFlow is very low-level language. Usually, you don't program directly in TensorFlow. Usually, we use Keras. Okay. Keras used to be separate from TensorFlow. There used to be this other, it's called a Theano. Sometimes in the old code, you see that this is based on Theano, T-H-E-N-O, something like that. But so it used to be that you could choose, if you use Keras, you could choose TensorFlow or Theano, they call the back end. But recently, Theano they stopped developing it because it's very similar to TensorFlow, and TensorFlow is backing of Google, so they have big resources, and so Google has kind of, or TensorFlow has kind of absorbed Keras. Okay, so what's the difference between Keras and PyTorch? Basically, they're both similar, but from reading, I was reading this book, from this book. Where is it? Deep Learning with PyTorch. So in here they say that Keras is better for beginners because once you call fit is where everything happens inside of the training. Okay, so it's easier to set up a very simple kind of a hand, if you want to classify, cats and dogs, it's easier to do in Keras. But PyTorch is better if you're a researcher, okay, and you want to really control all the details of the optimization process and things. So I would, and another thing they said it in this book is if you graduate and get a job and your boss asks you to make some kind of a AI application, then PyTorch is not so good in the real world. PyTorch is good in research, but TensorFlow is better supported for if you want to make a real application that's going to run in some company or something like that. Okay, but they both overlap. They both support GPUs, and I think PyTorch is supposedly stronger with natural language processing, but I'm not really sure about all the details. Wait. Okay, so that's PyTorch. So for today's lesson, well, first of all, I wanted to go back just a little bit to yesterday. We were classifying cats and dogs. And I just wanted to show you, I downloaded this from Kaggle. Okay, so when you download this, Kaggle is like this they have competitions. So you can join a competition and compete with people all around the world for who can get the best classification score. Okay, so when you download the data, everything is in this train, and you can see the name, the cats, starts with a cat here, and then down, if you go way down, is dog. So any file that starts with CAT, you classify as a cat. Anything starts with DOG. So in our program, we copied from this folder into this folder. So we copied, about 100 dogs and cats for training, and for testing, about 40. Okay, but there's another folder here. It's called a test. Okay, so this has files, but you see there's no cat or dog at the front. Okay, so this is unlabeled data. So if you were to participate in this competition, you have this file sample submission.csv, which if you open it, thank you. Start time zone. Okay. So you see here ID is 1, and the label is 0. Okay, so this is what you would submit to the competition. See, now they're all zeros. Okay, but if from this folder, test folder, this 1 is dog, right? So so you would probably, where is my enter a 1 there? Okay. Finalize. What was this one? I forgot. Yeah, this is another folder. Okay, this was used when you're done messing with your model. You say, yeah, this is my model. This is the best model I could possibly make. Then you don't want to divide your data into test and training. You want only training data. So that's what that folder is for. Okay. So for today's lesson, I thought there's another book. I think mostly we've been working in deep learning with Python. Okay. But there's another book here today. I want to use this book, Deep Learning for Computer Vision. Okay, so this book should be here. Okay, so we're going to come down to chapter 19 of this book. Okay. And we're going to work through some of these example code. So back
it's using
under
the fetch limnus,
deep
right?
learning for computer vision, you see code.
Oh, can you hear me? Hello?
Chapter 19.
Oh.
Right. So what I recommend you do is you copy this folder somewhere. Copy it to a folder of your choice. Okay, so in case you make a mistake and you want to go back to the original code before you started messing with it. Okay. David?
Yeah, can you hear me?
Hi, David.
Hello, can you hear me?
I can't hear you.
Yeah,
You're on mute.
No, I'm not. I think my audio is fine. I tested it.
What if it asks to unmute? Ask to unmute.
Okay, I'm unmuted again.
He's still on mute. It's
No,
okay.
You should be able to hear me. I tested my audio.
It's unmuted.
Yeah. So maybe you should turn up
the volume of mine. Mine is all the way up. Can you hear him?
Hello, hello. Can you
try
hear
turn
me?
your volume up.
Can anybody hear me? Hello, hello.
I can't hear you.
Oh, okay. I'll just be quiet.
Yeah.
I can hear you.
Okay.
Yeah, it may be a problem because I'm recording on my computer. So if for some reason, if you ask a question, I'll just repeat what you ask, okay?
Okay.
We'll work it out. Okay. Okay, so anyway, we're on this book, Computer Vision, Deep Learning for Computer Vision, Chapter 19. And we have copied the code. Okay, so we can go into, let me close this. Need this chat. Somebody chatted. Okay. So Spider, we can open presentation courses. Okay, chapter 19, number 1. Okay, so this is the first sample. So one thing in general, where it says from Keras, I think if you don't put a TensorFlow in front of this, TensorFlow, it'll make an error. But it depends. On mine, I installed TensorFlow, or excuse me, Keras separately. So I have 2 versions of Keras installed. Okay, but I think on Davidson's, it'll make an error if you don't add. Okay, so we can run this, and hopefully, pray. Okay. So you see here, it downloaded automatically the data set, and it plotted. Here you can see made a plot. So this is you can see here from Keras datasets. Yesterday we had the MNIST, which is the numbers. Okay, but this is very similar, but it's for fashion, just different shoes and shirts and sweaters and whatnot. So it's very similar problem, just a different data set. Okay. So that is number 1. So if we go to number 2, did that work? Did that work for you?
Actually, I put into the code. It was successful, but I can't see the dots.
Okay, let's why don't you share your screen so we can all, and maybe unmute yourself. Oh, your plots. What happened to your plots?
I'm surprised.
Hmm.
Surprised myself.
Files. You have files? Huh. Okay, we'll think about it. I don't know right now. Well, later we'll come back.
Right.
Okay. So I'll share my screen again. You should have this plots tab here. For some reason, your plots disappeared. Okay, we'll work on that later. anyway, the next step. So this is like I say, just similar. So this is in 10 classes. Okay, so we have t-shirts, trousers, pullover, and so on. So the first step here is very similar. We did it yesterday. Okay, so there's 60,000 and there's 10,000 for testing. They're 28 by 28 grayscale images like this. Okay. So the next step is we'll just go back to Spider. Load number 2, baseline model. Okay. So I'll just yeah, it might make an error here. Just try it. Right. Yeah, I remember I wanted to I'll stop this once it starts. This warning here is because I think in the model in the model
I think it's just the versions don't align. So I think where it says LR, you have to just replace it by learning underscore rate.
I think this code is a little bit old. One thing about doing an AI
Can you
is
hear
that
me?
if the code is 6 months old, it's already obsolete.
If you
So
can
I
hear
think
me, I
the
think you just have to
this
change
warning
LR
here
to learning rate.
is I'll just stop this and
Hello.
it should be alert. The name is changed from LRU's learning rate. Okay. So this LR, instead of LR here, it should be oh,
Hello.
check, what is it? Okay. Chat. You should change LR, yeah, exactly. Thank you, David. Okay. Now I want to put a breakpoint here at step. See if this works. Okay. So step into, okay, step into, okay, so this is the same as yesterday. We load from Keras, this fashion, and then we're going to reshape. So if you remember from yesterday, train X now, train X. Okay, there's 60,000 28 by 28 images, right? But this doesn't specify RGB or a grayscale. So we want these images to be grayscale. So we're going to add a 1 here. See, now there's a 1. The same way with the test data. We just have to add a 1 here so that it knows that it's a grayscale image. And then this is a review from yesterday, train Y. If you look at this, it's these are the labels here, but we want them to be in vector form. So train Y now is in a vector form like this. Okay. So that's what they call a one-hot encoding. Okay. So now, prep the pixels. This is the same as yesterday too. We just train now is an array of uint 8 here. Right. So we're gonna convert that to a floating point. So now train normalized is a floating point array of floating point values. And same for test. And then we're going to divide everything by 255. Okay. So that's nothing new. Then we're going to evaluate the model. Okay. So what are you going to evaluate? So here again, he uses this called a k-fold, right? So he's going to run this 5 times and display the output. Okay, so I want to run this up to right. So here, see this train IX. Train IX. You see it's 1200 now. Okay, so this 12,000. Test IX. Excuse me. Test IX. Okay. So I think what this code does is it's easier to see with a test is that it's going to take a 1/5 of the data. 1/5. Okay, so now train X and test X. Test X, 12,000. Test X. So basically, yeah, it's kind of confusing, but it's sending a 1/5 of using 1/5 of the data for validation. All right. So if you scroll over here, okay. So this is where I was saying sometimes you mix up the names. I think this really should be a validation X instead of test X. Personally, I like to keep separate validation and test. Test data is data that you hold back from all the training process, right? In fact, sometimes I've seen in medical papers, the test data they'll get from a different hospital. So that's really the best way to do it is the test data you want to completely hold back and even if possible, get from a different source. So that's a more fair comparison. But you can see here he used test X for validation data. So you just be careful. If I were rewriting this code, I would rewrite this val X and val Y. Okay. But anyway, that's kind of a pedantic. Okay, but this takes a little bit too long to run, so I'm going to stop it and come back here to the book and scroll down. We're going to fit with the validation data we saw here. Here you see, calls it val X, val Y, right? So this is the good way, the proper way, so you don't get confused validation and test data, right? So k-folds, right? So develop the baseline model. Okay, we loaded the data. We one hot encoded. Okay, now we prepared the pixel data. And now we're going to define the model. Okay, so here it's the same as yesterday. Remember, we have a convolution 2D. So I like to think of this as like edge detection filters. Okay, if you're familiar with image processing, then edge detection filters are very you understand. So this the input size, input shape is 28 by 28 by 1. So the grayscale images. And we're going to initialize with random numbers. And we're going to use ReLU. We always used ReLU for inside the network. But this 32, so what is that? This is what I was saying, a hyperparameter. But what I like to think of it is that it'll make 32 copies of the image. So you have a 28, but you're going to apply 32 different filters to each image. Okay, so one might, for example, usually you have a horizontal edge detection filter that can detect horizontal edges, and a vertical edge detector. Right. So so this 32 here, I think of it as 32 copies of the same image, but with different filters applied. Okay. And then max pooling is to kind of reduce the data. We have too much data, so let's kind of reduce a little bit. And then before we can pass it to the what they call a fully connected layer, we have to flatten it. So just take each row and tack it onto the next column, make one long or one tall image, however you want to think of it. And then this number 2 also here is a hyperparameter, which just from experience depends on how much data you have. Okay, in general, a smaller will be faster but larger may be a better result, but not always. Okay, so come down, and here you see he didn't use Atom, he used the SGD, and the LR should be a learning rate here. And I think these are the default values here, so we won't worry about that. Okay, and this is categorical. We have 10 different categories. Okay, it's not a binary yes/no question. So be careful. Don't make a mistake like I did and enter a binary cross entropy here. Okay, so we will evaluate it. So this has to run 5 times. So it takes it's kind of slow, but if you were patient enough to plot the results. Okay, so here's the complete code. Okay, okay, you can see here it ran 5 times and it is around a 91%. Okay, and here are plots here. You can see overfitting here a little bit. Okay, so, and then the accuracy. So if you are writing a paper, you want to present the accuracy like this. Okay, you have a mean, standard deviation, and number of times you ran. Okay, so be careful. Don't just say, well, we got 91%, because the reviewer should come back and ask you, well, what was your standard deviation? How many times did you run it? Okay, and finally the whisker plots here. Okay, I think this is the min and the max and a standard deviation on this plot here. Okay, any questions? Make sense? Too easy? Not too easy. Easy enough. Okay, so now we want to make improvements. So that was our baseline. Okay, so now we're going to make improvements. So one improvement that talked about it a little bit yesterday was padding. Okay. So what is padding? So remember, padding is we're going to put zeros around the edge. Okay, so the reason you do that, you think, well, that was kind of a waste of memory. Okay, you're kind of expanding the image, making it larger. So why don't you just in a loop in C, you could just write a for loop to pad zeros. But with we're dealing with GPUs. Okay, GPUs like to do things in parallel. They don't like little loops, right? So it is a waste of memory. Okay, but remember we can do the whole image in one parallel process. We can take the whole image, multiply it by this filter kernel, and boom, we have the same result. Okay, so that's why this padding is popular. Okay, so this way, so now so first of all, I want to go back. Chat. How many times should we run an experiment? I mean, I would say at least 5 times, at most 10 times. How many k-folds for it to be acceptable? Yeah, I would say 5 is acceptable. Yeah, good question. Okay. So what I want to do is go back here. You see we defined the model, right? So what I want to do here, I want to add a print model summary, right? What's wrong? What is this? Okay. Okay, then I want to put a breakpoint here. And then I want to debug, not run. Okay. What happened? What happened? Oh, I had another breakpoint down here. Okay, now I want to continue running. Okay, so now I'm here. Okay, so now I have a printout of my model here. So we're going to refer back to this. So I'm going to copy this, and I'm going to paste it somewhere. Where is my notebook? Where's my notebook? Notebook. I usually keep a okay, let's do it in here. We'll just make a new file and I'll do it here. Wow, colors. Okay. Okay, so that was baseline number 2. Okay, so now I want to stop this. Now I want to open up number 3. Baseline was padding. Okay. Now the only difference in this baseline was padding is here in the model we added padding. Where is it? Oh, here it is. Padding. You see this padding same on the convolution. Okay. So what I want to do is I want to do the same thing here. I want to do the same print model summary. Print model summary and put a breakpoint. Okay. Then I want to debug, not run. Okay. Instead. Okay. Now, what I want to do is copy this. Okay. And then we can compare. Okay, so now you can see you remember our input shape was 28 by 28. Okay, so the original code with no padding, you see that this is the output shape from this convolution. Okay, so it's a 3 by 3 kernel. Okay, so that means that it will lose 1 pixel on the left to right, the top and bottom, because it cannot compute the filter at the edge. Okay, so the convolutions generally make the image a little bit smaller. Okay, so if it's 3 by 3, it's going to lose 1 pixel. Okay, so it's 5 by 5, it's going to lose 2 pixels on each side. And if it's 9, and so on. Okay, so here you can. Okay, then the next step here is 13 by 13. Okay, that's because remember max pooling is going to take a 2 by 2 block and find the max value and use that for 1 pixel. So the resolution is going to be half. So that's why 13 is 26 divided by 2. You see there. Okay, and the 32 is because that's just what the 32 here, the hyperparameter. It's just an arbitrary number we decided. So, but I think of it, like I said, make 32 copies of this image and apply a different filter to each one. Okay, so we go back here. We can see that total parameters, right, went up a little bit. We had 500,000, 542,000, and 628,000. So just it's actually only adding this. It doesn't make much difference. This is not a big change, small change. And if we go back to our book here, where are we? All right. Okay. This is the. All right. Okay. He says doesn't make much sense. Okay. So we show a very slight increase. Okay. Went from 91.2 to 91.1. Okay, but that's actually within the standard deviation. Okay, so it may not even be an actual improvement. Okay. 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 Go on. Okay, so let's go on to the next step. Increase filters. Increase filters. So here we're going to add another layer. I think I forgot number four filters. Okay. Right, so here he just increased from 32 to 64. Okay, so now if we do our same trick, we'll come down, and before we start training model, go to print model summary. Okay, put a breakpoint here. Okay, debug. Is it working? Okay. What happened? There it goes. Okay. Okay, so now we want to copy this. Whoop, whoop. Here. Okay, copy. Okay, so this is our third version. Okay, so the main thing you can see here is that these numbers are the same, but you can see the total number of parameters is now over 1 million, where before we had about 500,000. Okay, so that makes sense. We doubled the number of convolutions, and we have doubled the number of total parameters. Okay, so this total parameters is a good gives you a good estimation how large your model is and how long it's going. The larger the model, it's going to take longer to train. That may or may not have a better result. Okay. So what was the result from this? So go down. What was this one? Okay. Model Linker shows there's some further improvement over baseline. This case shows the models will have a reasonable fit problem with a small sign. Some runs overfitting. So yeah, so we are getting overfitting still. Okay. So we did have a small decrease, showing a possible decrease in performance. Okay. Maybe we're now at 90.1%. Okay, so but still maybe it's within the bounds of the, it's not clear within the standard deviation. Okay. Okay, so we'll go on, make the final model. So now we're done messing around with all our hyperparameters. And we're going to train the final model. Baseline padding. Did I do number 4? Yeah, we did 4. So 5, save the final model. Here. Okay, so you see in this example, he doesn't use any of the what's it called, K-harness, or there's no dividing up the data, just all the training data. Okay, we're going to use it, all the training. Test data is still separate, We can use, we can test it at the end. Okay, but this takes, I ran this, I did it this morning, and where is it? Oh yeah. Okay. So if you have time, on my, I ran it on my GPU this morning, and it took a couple hours to run the final model. But for today, we'll just cheat and copy. Where is it? Okay, chapter 19. Okay, so if you run this, say number 5 here, then you should get this final model.h5. Okay, that's your homework assignment. When you go home, you can start it before you go to bed, and when you wake up, you should have your final model.h5. Okay, so if you have that, then you should be able to run this number 6 here. So number 6. Number 6 here. But what I could do is I'll just give it to you. If I here, I'll be nice. And I'll upload this file to presentations, courses. lectures. Okay, we're in chapter 19. So what you need is this file. How big is it? 4 megabytes. No problem. Okay. So there is your file. So if I share this, anyone with the link, copy the link, then I should be able to chat. It is chat. Chat, yeah. Okay, you should be able to download that H5 file. And then you should be able to run number 6 here, which is yeah, this right, this uses the test data. So remember for MNIST, they separated. They have 60,000 for training and 10,000 for testing. So if you run this, I don't know how long it'll take on this computer, but not long. Okay, so very fast. So it tested 10,000 times, and it got over 90%. Not bad. Okay, and then the last sample program is make a prediction. So this uses a sample image ping, sample ping. So this is our sample image. You notice this is a very high resolution. This is 740 pixels. Okay, so we're going to have to shrink it back down to 28. Okay, so that's where you see it does is reshape. So let's just step through this. This should be very easy. Let's see what's happening. I think one problem. I think I forgot to stop this. Exit. Keyboard. Yeah. I think I got these control. Copy text. This. Okay, I think I'm gonna have to restart my spider here. Sorry. No, I don't want to say that. 30. Sometimes spider gets confused. I think it's because I'm running different programs without stopping them first. Okay, so that's spider. Where is it? Here we go. Spider. $30. Supposed to go to 4:15. Okay. Yeah, let's try this again. Number 4. Takes a while to load Keras. All right. Yeah, I remember now. Okay. The reason I wanted to show you this is because this code, right? Okay, so this is another case where the code is a little bit old. So it cannot load from processing image. So if you get this error, what you do is you copy it into Google, and it will take you to Stack Overflow. Right. Stack Overflow. Okay, you come down and you see they've moved. What you want to do is this. Copy. Okay, instead of pre-processing image, it's now in Keras utils, TensorFlow Keras utils. And the same way with this one. We want to rename this guy. Oops. Go. Okay, we want this image to array. Image to array. Okay, now if I run this, I don't want to debug this yet. If I run this, we're going to get another error. Okay, this time it says attribute error. Okay. This one is a little trickier, but I'll just tell you, the problem is that this predict classes no longer exists. Okay, this is code is too old, and after messing around a bit, I came up with this solution here. This is another version here. Okay, so what you want to do is this. You don't want to do predict classes. You want to do it like this. And you have to do it in 2 steps now. And all right, and this uses NumPy, so you have to import NumPy as NP. Okay, so now rerun this, it should work. 2. Okay, so let's step through this one time. Debug, run. Okay, step into, step over. Okay, reload the image. And the model we're going to load from the file there. Then we just call predict. Okay. So predict. Okay, so now result. What I want to show you is a result here. Okay, so this is what predict returns. You can see it's like 99% sure that this is number 2. Okay, so what was number 2? If we go back, if you remember, number 2 was overcode or something. Evaluate the final model. Okay, we did that. Make a prediction, right? So this was our sample image. And we resized it 28 by 28. And then the result 2, right? Right, so I wanted to show you predict returns something like this. this vector. Okay, but this argmax is part of the NumPy library. So that will just find the maximum value and make the result like this. Okay, but you notice it's still an array. This is an array of integers, but it only has a one value here. Result. That's why a result you have to put in brackets here. Okay, so normally we don't deal with just one sample. It's much more efficient is to gather all your samples up and then boom in one. So that's why the result is an array here. Okay, but if we put a brackets, we get a single value here. 2. You see, I got a 2 here. Okay, so if this were a real application, then we would look up to the text for that would be over code or something. As you remember at the beginning, where it was. No, I'm all lost. So this is chapter 19. I lost my place here. To go back here. Go back here. Okay. Right. So number 2 is a pullover. You see here. Okay. So if this were a real program, you would put this into a table, these texts, so convert the these indices into a text. Okay. But that is a homework assignment. Okay, any questions? Make sense? Okay, so let's go on. The next sample, the next chapter in here. Right. So if you remember from yesterday, we had this example from Stanford University that classified these small images. And I mentioned that they are from a CFAR10. So these are small images that have been collected with labels. So again, it's pretty much the same process, but we'll go through this chapter step by step. So again, I like to copy chapter, now this 19 or chapter 20. Chapter 20 we want. Okay, so copy chapter 20 somewhere. Paste. Okay. So CFAR. Right, so here, here are our categories. Remember, there's another CFAR 100, has a 100 categories. So if you get ambitious, you can try CFAR 100, but start off CFAR 10 here. Okay, so so Spider, you can close all this stuff. Close, 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 close. Okay, I went one too far. Okay, good. 20. So chapter 1, load the data set. Okay, so here it's going to use this data set. So if I run this, you should see it download. Maybe if it's the first time. If you never downloaded it before, you'll see it download. Okay, so now we have, instead of 60,000, we have 50,000 training images. And they're a little bit larger, they're 32 by 32, and they're 3 planes, so it's RGB. Okay, and if you look at our plots, here we can see, I wonder if preferences, I was thinking what happened to your plot tab. Maybe there's a preference. You accidentally turned it off. Later we'll Google how to turn on my plots in Spider. Okay, we'll deal with that later. So let's go number 2 here. Okay, so this is more of the same, but the only difference, as far as I know, okay, step into, okay, going to load from the side far, right? Then we're going to train Y, do the 1-hot encoding. So that's the same. And then we're going to prepare our pixels. Should be same. Okay. So even though we have RGB now, color images, this routine is exactly the same. Just convert it to float and divide everything by 255. So this is one of those things that Python you can do. If this were a C program, you would have to make a little for loop to do this. Okay. So define the model should be the same. What happened? Why is this hiding? I don't know what happened to my model. Hidden. Sequential. Right. Okay. This is going to take too much time. So I'm going to stop this and go back, not here, to here. Okay, so we have birds. Okay, so this is the load. Okay, here's our plot. Okay, did this. We did this. We did this. Define the model. I wonder why just this sequential. Evaluate the model. I'm wondering why this just shows 10, 10, 10 here. Dot, dot, dot. I can't figure out what's wrong. Where's the rest of my model? Fit. Serious? If we define the model function below. Return the model, we can fill in it or replace
Can you hear me?
or give a model that we wish to evaluate later.
Can you hear me?
Okay,
Hello, hello.
so it doesn't really actually define the model yet.
Yeah, that's what I was going.
Okay. Diagnosis, this is all the same. A complete example. Okay. Okay, he didn't actually define the model yet. I see. Now we're going to define the baseline model. Okay, which is going to look similar to what we had before, but here he's going to have two layers of convolution networks. They're both going to be 32. Then the max pooling, max pooling, and then another layer was 64. Okay, then or max pooling. Okay, so he's going from 32, 64, 128. Okay, so what he's doing is the images are getting smaller, but we're increasing the number of convolutions. Okay, so it's kind of a this is a common structure for classification networks. Okay, then we're going to have a flattened and our fully connected layer, 128. Okay, this is the same. Compile the model here. Okay. Okay, so okay, so this is the baseline 1 VG. This is we say VGG 16 is because it has 16 of these convolution layers. Okay, so this one has a one layer, sort of a baseline. So you can see how it works. Okay, so if we ran that, we would get about 67% accuracy. Okay. And we could plot. You see our entropy is not going down. This looks pretty bad. Okay. So what about with two blocks? Now we have 32 and 32 here. Okay, then goes up a little bit, over 70% here. But plots do not look healthy. This should go down, and this should go up. Okay, this yellow line does not look very healthy. So 3 blocks. Okay, so he did 32, 32, and then a 64, 64. Okay, and then 128 to 128. Okay, I see. So 3 blocks. What does that do? Went up to 73%, but still doesn't look very healthy. Okay, so from 1, 2, and 3 blocks, we did see an improvement of the accuracy. Okay, how else can we improve it? So dropout is going to help us prevent the overfitting. Okay, so here drop out, you can see a 20% dropout here, and another 20% here, another 20% here. Okay, so that will do what? Okay, so it's getting better, 83%. Okay, so now this is starting to look a little more normal. Okay, a little bit of overfitting still. So data augmentation. So remember the first choice is dropout. It's the easiest, add dropout layers. Okay, the second choice is augmentation. Okay, so if you remember from yesterday, the easy way is to use this called an image generator, image data generator. So think of it, image generator, instead of reading your data directly, this generator kind of sits in between the fit and your data. Okay, so we have a shift range is up 10%. So the maximum 10% on the width and the height and the random horizontal flip. Okay, so you remember these are images of, they're not just dogs and cats anymore. Now they're airplanes or cars. Okay, but you can think of any of these images that we flip horizontally, it'll still look like a normal input, right? But a vertical flip might be strange, right? So that's why we only use a horizontal flip in this case. Okay. So if we ran that, then with data augmentation, okay, now we're up to 84%. Okay, so that was a pretty big jump, almost over 10% improvement using data augmentation. Pretty good. Okay, so these graphs still have a little bit of overfitting, but what else? Dropout and, oh, here and augmentation. Okay. So now combining the two, and I'll get up to 85%, 86%. Okay, so now this is looking good. This is what you want your graph to look like. Something like this. Okay. Dropout and batch. Okay, I haven't talked about this batch normalization yet, but I think here you see this from batch normalization. I think it prevents your weights from getting too big. Okay, after each epoch, it will normalize your weights. So this batch normalization adds it in between each block here, or after each convolution layer. Just add this batch normalization. Okay. So what does that do? Okay, so now we're almost up to 89% from 85%. Okay, so another good sign. Okay. So reviewing the learning curves shows continued improvement during 400 epochs. Okay, now he ran it for 400 epochs. Okay. And got a good result. See a slight drop off. Further testing. Okay, looking good. Okay, so this adding these different techniques, we're getting up close to 90% accuracy. Okay, so make a final, save the final model. Okay, again, I think I ran this morning. This is chapter 20. Yeah, chapter 20. The final model, yeah, the same. Okay, so I'll leave that. Well, what the heck? I'll same file name. I wonder what will happen here. Okay, let me file upload. This is chapter 19, chapter 20. Okay, I'll replace that. You have to remember the first one was for chapter, okay, chapter, okay. So I think the link will be the same. Share. I think the link is just the same. So if you're interested, you can just download this. But remember that this goes in chapter 20. Yeah. If I chat. Yeah, it's just the same link. Okay, but if you save that in chapter 20, then you should be able to run this number 11 here, which is here. What's this? Okay. 11. Okay, this is going to load one image, which should be here. Right? Boy, it's hard to tell. What is that? Let's see what happens here. Then we're going to have the same problem. Okay, as before, that we're going to have to okay, you have to fix it to this. There is no more pre-processing image. Okay. No more pre-processing. Then we have to do like this. Same. No more predict classes. Like this. And then we have to remember to import by as in people. Right. Okay. Then oops. Have it in the wrong folder. Maybe I forgot to copy this. I forgot to copy this. Okay. Then you run it. The output of 4. I think it's supposed to be a deer. What is number 4? Let's see what he says down here. Make a prediction. Right? It's supposed to be a deer. What is number 4? 4. Yeah, so that's correct. A deer. It worked. Amazing. Okay, any questions? We have about 10 more minutes. What else do we have in here? So by the way, if you want the other things, for example, pixel scaling, we scaled the pixel 0 to 1. Okay. Another thing that you might try is to find the mean value. Okay, and make that 0. Okay, then you'll have minus and plus. In general, when training these networks, you want your data to be a mean of 0 and a standard deviation of 1. Okay, for some reason that makes training easier. Okay, so you may, if you're curious, you can try that. Okay, but the problem is that we'll see. I think we'll see later. You have to remember what your data was trained, what the mean was. Okay, so when you input a new image, you have to remember what that number was. Okay, it's usually around 128. Okay, is gray between 255, the middle, but it might be a little bit different. You have to make a histogram of all your input data. Okay. And maybe you have some small improvement. I don't think the improvement will be large, only a small improvement. And learning rates. There's actually one of these books. There's actually a whole book about learning rates. If you're really serious about learning rates, which one was it? Oh yeah, this one. Yeah, I was reading this morning. XBoost. I've never. This book here, the very last one, XBoost. XBoost is a kind of a super advanced gradient descent. Okay, normally if you just use Atom, it's easier, takes care of everything. You don't have to think about your all these parameters, right? But if you really want to investigate the best way, when you get your training times become really large, it really becomes important how to the best gradient descent algorithm. Okay, now we're just doing little training exercises. It's no big deal. But when you get serious about AI, then you might consider something like XBoost and all these advanced learning rates. Okay, and yesterday we saw transfer learning, right? So I would recommend that if you have a new project, say you have some sample slides or something your professor gave you, this big folder full of images, right? You could train it from scratch, but probably transfer learning is going to work better, because remember it only uses the left half. It keeps the left half of the VGG network, which is all the filters, which is all the edge detection, right? So you think about, well, there's no reason to relearn all of that, right? But what you need is a classification. You need on the right-hand side, you have the fully connected layer. If you recall from yesterday, so you just have to train the classification part. Okay, so that's transfer learning. Okay. Okay, we have 5 more minutes. Right, so here's we did yesterday cats and dogs. So I'll just skim over this chapter briefly here. You can download it. You don't have to download this because I already did it for you. Right. So there are dogs. Here are cats. Yeah, now in this chapter, it's not total copy paste from the previous book, but some things. Yeah, one thing he does differently here. This section is pre-processing the photo size optional. Okay. Here, if you recall, we read off from the folder. We read our data in from a folder we use as a data generator to read from the folder. But it actually faster if you can gather all your data into one file. Here is called this NumPy file. He just appended all the images into one file. So, but you need at least 12 gigabytes of RAM to do it this way. So so in general, I would say that if you have lots of RAM, try it this way will be faster. Okay, it's faster than reading JPEG files from the hard disk. Okay, but if you have millions of images, eventually you're going to run out of RAM. Okay. So this is the same, cats and dogs. See, I wanted to say something about the seed here. He sets a seed to 1 here, which means every time you run this, it will always generate the same result. Usually what you want to do is replace this 1 with a time, get the current time and use that as a random number generator seed. Okay, so if you ever worked with random number generators, they're not really random. They're just a clever algorithm to generate numbers, and every number depends on the current number. Okay, so it's just a simple algorithm, right? They're not. That's why they call them pseudo random. Okay, but if you're debugging your program, you don't want too much randomness. Okay, so if you hit a bug, you want to be able to hit that bug every time. So in that case, you want to set your seed to something constant. Okay, but normally you don't want to do this. You want to put time in here. Okay, so we trained baseline. This is all review again. Moving scale. The best is 1 block VGG we saw. And then 2 block VGG. And 3 block VGG. Okay. And you see improves. And then drop out. And drop out. Okay, getting better. Augmentation. Okay. It's even better. Okay. Discussion. He doesn't talk about normalization for some reason in this chapter. Okay. Transfer learning, right? So here, it's kind of tricky. You have to set your layers that you want to keep. You want to set this trainable to false. Okay. It's kind of tricky, but it's very powerful. And here, yeah, this is what I was talking about. This pre-trained, if you use this pre-trained VGG model, you have to somehow know that that uses these numbers. This is the average pixel value for the R, G, and B that they've used to this is what you have to set to 0. Okay, for the red, for every time you read an image, instead of scaling from 0 to 1, you want to set 123.68 for the red, what do you call band, to 0. Okay, so it's kind of a tricky here. Okay. Also, if you use a pre-trained, you're stuck with this size 224, 224. Okay, you have to use this image size. Okay. So here is the data generator mean. That's what these 3 numbers here. It's because of the VGG network that we're used these values. So I wish that this was stored somehow in the VGG, and it would just do it automatically, but it doesn't seem to be stored anywhere. You just have to know this. Okay, so let's take a break, 15 minutes, and we'll come back at when in 4:30.